Before we can jump headfirst into the amazing and sometimes confusing world of the medium, we need to explore the tools that people use to understand and explain the world around us, their power and their limitations. Modelling is an attempt to explain the world and predict future behaviour. A model is only as good as its predictions and the insight it reveals. John H. Miller and Scotty Page said that learning about modelling is a lot like learning about sex. Despite its importance, most people do not want to discuss it. No matter how much you read about it, it just doesn't seem the same when you actually get around to doing it. So whilst I will try to explain what modelling is and how it works, there is just no substitute for trying it out yourself. A great model will simplify a situation enough so that it can be easily understood, yet not so much that the results are so far from reality as to be useless. Of course, there is a trade-off between simplicity and usefulness, a fine line that all those wanting to explore the medium must carefully tread. In physics, models are usually mathematical, and without purposeful training can be hard to interpret. But as our system becomes more complicated, consisting of many parts, and in turn potentially more complex, we need to expand our toolbox. Only then can we explore other avenues to gain insight into the natural world. Besides disrupting the social fabric of our society, technology like computers have allowed us to explore more complicated models and ask more complicated questions. But first, some simpler questions. What is a model? What does it look like? And how does it work? Let's explore a relatively simple type of model that most of you will be familiar with. A map is an attempt to represent features of the natural world that can be used to form insights and make decisions. For example, a roadmap will tell you how to get from A to B, whilst a map of the position and density of coffee shops in your city might help you to decide where to build your own hip, single-origin coffee shop. A map of my room would tell me how to get from my computer to my computer. A good map does not have too much detail. A map with every possible feature in a given space would essentially just be a black sheet of paper, whilst a map with no features would be a white one. So again, we are struck by the need to only include the most pertinent features in our model to keep it simple and useful. Now let's explore a slightly more formal and maybe a little mathematical explanation of modelling and how you might do it. I will keep this as simple as possible, and I promise that the mathematics involved will clarify rather than confuse. Let's say we have a system at some current time t, and we want to know what the system will be doing in some future time t+1. This could be a system of humans making decisions about how they will spend their money, or a system of proteins moving around the body performing various protein tasks. Something happened in the time jump that can be explained by some function. Let's label this function f. If you don't know what a function is, think of it as a machine that takes some input, in this case the features of the system at our present time t, and outputs what the system will be doing in the future time t+1. The problem is, we don't know what f is, and so we need to come up with what we think it might be. We need to come up with a model. This part requires a lot of patience, insight, and creativity. To illustrate this model of a model, let's use the weather as an example. At a time t, we need to know the speed and position of every atom in the atmosphere. These are our inputs. But this is hard to know and would result in some hefty calculations. So instead, we might consider some other indicators that are equivalent to knowing the speeds and positions of every atom. These might be something more easily measured, like the humidity and temperature at each point in space. We then need to come up with some new function, our model, that takes the humidity and temperature as inputs and outputs something that is close to the actual behaviour of the weather at t+1. This function, little f, represents the laws of physics that govern humidity and temperature. So to continue with our model, we need some function e that takes the state of the system, i.e. the positions and speeds of each atom, and converts it to the variables we would prefer to deal with, humidity and temperature. We then take the output of e, the humidities and temperatures, and these become our inputs to our model, little f, and tells us what will happen in the future at t+1. Little f is analogous to big F and acts as our model. If little f is any good, then the following equation should hold. This is basically saying that the humidities and temperatures predicted by our model f should be the same as the humidities and temperatures determined by the laws of nature, here denoted as big F. You might like to pause the video and ponder this equation. In any case, the only way to know if your model is useful is to wait until time t+1 and compare its prediction against the real result. If they don't match up, we clearly have some work to do on our model, f. It is important to highlight that something like Newton's laws of motion are just models. They predict really well how a ball might roll down a hill, but tend to fail as speeds get close to that of light. We should also note that while many laws of nature are taken to be irrefutable, they are just models. At best, they're extremely accurate approximations. Modelling is so important in any scientific endeavour and is crucial in creating a concrete understanding of nature. Whether it be designing the wing of an aeroplane so it doesn't fall out of the sky, modelling the spread of disease to better optimise global health, or deciding where to build that new coffee startup, modelling is an important tool when dissecting the messy world of the medium. Now, if you want to know some more about modelling and want to delve into some of the computational models used to explore complex social systems, check out John H. Miller and Scotty Page's book on complex adaptive systems. Much of what we just discussed is outlined in Chapter 3. If you enjoyed this video, don't forget to subscribe, and let me know what you'd like modelled in your life in the comments below.